any link. So a fiber optic link, it comprises of a transmitter, we have a receiver, and in between we have the fiber. And in any system, you have one source, you have one detector, and you have to couple your optical source to the fiber. You have coupled your optical fiber to the detector, but at one time. But in between you have a long length. It may be 100 kilometer, it may be 500 kilometer, it may be 1000 kilometer, it may be 10,000 kilometer. But yesterday we discussed the fibers. The fiber available are not of that much length. You will get maybe 5 kilometer of the fiber cable, or 4 kilometer, 5 kilometer, maybe in this range only, maybe maximum 8 to 10 kilometer. So it means if you have a 100 kilometer link, you need number of joints. So joints are inevitable in any of the communication link. It is not only with the optical fiber, even in the electrical system also. And we also know at each joint there is a loss. Some loss is always associated with each joint or each connection. And it is very, very important in the optical communication system that this loss should be as small as possible, because here we have limited power. You cannot launch any amount of power in your in the optical fiber. Otherwise, non-linear effects will start affecting the system. Linear effects, they are easier to control, but non-linear effects, they need special type of mitigations. So usually one try to avoid the non-linear effect. So in this system, you see there are the technical requirement for both jointing and termination. Termination is the connection which is demountable. At some places I need the termination. For example, with source and fiber, I may need the termination. At the repeater, wherever we have to put the repeater, I need the termination. Sometimes I have to dismount the system. So both depending upon the requirement, there can be joint. When I am saying joint is a permanent joint. It is similar to welding or soldering in the electronic system. And connection or termination, it is demounted. So the number of joints or connections, so it depends upon different parameter. One is link length between repeater. So at the repeater, you have to break the fiber. You have to make the termination. So you have to connect your fiber to certain device. Repeater is nothing but it is a full-fledged system. It is at the repeater you have an optical detector, you have an amplifier, you have a light source. So you need the termination at the repeater. So it depends upon what is the repeater spacing. And repeater spacing depends upon type of fiber, type of source, and the data rate. Then continuous length of the fiber. What is the length of fiber spool available? Maybe 4 kilometer, 5 kilometer, or 8 kilometer. You will not get any spool of fiber more than this length. Generally it is 4 to 5 kilometer because of the all transportation problems. Then length of fiber cable practically or conveniently installed as a continuous length. So it is not possible to lay the fiber in a single stretch 100 kilometer. In between, somehow if fiber is available, we have to intentionally break it. But there are practical limitations. During the installation, you see the fiber, the machines they are using, you can pull the fiber maybe up to 1 kilometer or maybe up to 2.5 kilometer. So these are the installation issues. So all these are the parameters for the number of joints. So repeater spacing, you see it is a continuously increasing parameter. We want it to be as far as possible, because each repeater it adds to the cost. More the number of repeater, more will be the cost added. So it again I mentioned it may be 60 kilometer, it may be 100 kilometer, it may be 300 kilometer, depending upon the type of fiber or data rate. Okay. So where I need the joint? So I need a joint at source to fiber. I need a joint between fiber to fiber. I need a joint between fiber and detector. But there are a number of joints between fiber to fiber. Now when you are coupling your source to fiber, if you are not very experienced, with small mistakes you can damage your source, because it is a very, very expensive part. Normally in communication we use the light sources for high performance. They are the DFB laser, distributed feedback laser. A normal DFB, it costs around 2 lakhs. You can look the cost by. So if you are not very, very experienced, you may damage the source. Similarly, if you are not very experienced, you may damage the detector also. And if you are not perfect in the coupling, if your coupling is not perfect, you will lose large power at the coupling itself. So as a result, the manufacturers, they provide you what you call as the electro-optical devices, sources and detector with fiber optic pigtail to facilitate direct fiber connection. What is pigtail? Have you seen the pig? It has very small tail. So they will put small fiber over the detector, over the source. They will put the fiber, maybe 1 meter or half a meter length of the fiber. So now you have to join the fiber to fiber. You can join your fiber with the pigtail at the source. You can join your fiber with the pigtail at the detector. So now job is to fiber connection. For any communication system, the main requirement is fiber to fiber connection with low loss and minimum distortion. So we will discuss only now with the fiber to fiber connections. So what is my requirement? Minimum loss, minimum distortion. So we will see what are the mechanisms that lead to losses. If I am familiar with those parameters, I will take care during this operation. So in fiber there are a major two category of joints. I mentioned one is the fiber splice. So splicing is a permanent or semi-permanent joint. It is similar to soldering. On the other hand, we have the fiber connectors. This is the termination or demountable or removable joint. So this is similar to our plug and sockets in the electrical system. Nowadays, sometimes we also need another category, what is called the fiber couplers. Couplers, these are all branching devices, either splitting or combiners. They split the signal, they combine the signal. The requirement came because of the importance of networks. Now we are working in the networking. We are collecting the information from number of users. We are distributing the information to number of users. So we need, these are also the optical devices. A coupler is a totally optical device where it is made from different type of fibers. So you can see here, you have input fiber, you have number of output fibers. You have number of output fiber, input fiber, single output fiber. So how you make join the fibers in order to create the coupler? In between there is a intermixing region. So this is similar to a joint. It is similar to a splicing, but in different configuration. It may be a one to many port. It may be a many to one, or it may be a 4-port coupler, 8-port coupler, or depending upon the requirement, 32 port, 64 port. So again we need the jointing here or splicing here. So then now we will come to what is the crucial aspect of fiber joint concerning optical loss. Why the loss occur? at the joint. So the main criteria is the fiber alignment. The light travel in the core only. So you have to align the core. If there is any mismatch in the core, that part of energy will be lost because the light undergo diffraction. So that will be lost there. So let us see what are the mechanism for the loss at the joint. What are the different parameters? So loss mechanism at joints. One is the Fresnel reflection. When light comes at any interface, it undergo reflection. Reflection may be small, reflection may be more. It depends what is the type of interface. How much is the change in the refractive index at that place? So it depends on the refractive index at the interface. So Fresnel reflection is the optical loss encountered at the interface. Even when two fiber ends are very, very smooth or perpendicular to fiber axis or perfectly aligned, still there is a Fresnel reflection because there is a change of refractive index. So it encountered. So a small proportion of light may be reflected back into the transmitting fiber, causing attenuation at the joint. So fiber, it is called Fresnel reflection, and you see it is at two places. Now you have a fiber, you bring the another fiber to near to each other. In between there will be either air gap, or you will use some epoxy to make a joint, or you will fuse the fiber, two fiber. You will heat the two fiber and you will fuse it. When you fuse the two fiber, the strength of the fiber will change, of the fused fiber will be different from the unfused fiber. So some change in refractive index will take place. So it depends how much is the change in the refractive index at the interface. So it occur at two places. Light will come from fiber, it go from one refractive index to other. So there is a Fresnel reflection. Then it will go to air, from air to fiber. Again there is a Fresnel reflection. Again there is a change of interface. So it occurs twice at a joint. Okay. So glass to air, air to glass. So we have to see that it occurred twice because it can be calculated by different formulas. So this is how the Fresnel light reflection of light can be evaluated at the single interface. So how much light will be reflected? That is your N1 minus N over N1 plus N square. This comes from the Fresnel equations. N1 is the refractive index of fiber, N is the refractive index at the interface, and if there is a air, N will be 1. So Fresnel reflection depend upon the refractive index of the fiber and the material. So when this R to be minimum, I want this R to be as small as possible. It will be minimum when your numerator is minimum. So N1 minus N, small it is, small will be R. So I can calculate the Fresnel reflection at the interface. So when you are evaluating the Fresnel reflection, you have to evaluate it twice. One from N1 minus to N, again N to N1. It is in the square form, so it hardly matters. So we can calculate how much is the Fresnel reflection at a interface. So this is the one of the loss mechanism, and we can calculate this loss Fresnel equal to minus 10, because losses are always taken negative, minus 10 log 1 minus R. This is the power. So this is simple of a decimal formula. My decibel is 10 log P output over P input. What is my P input? Let us say 1. P output 1 minus R. So it is 1 minus R over 1. So I can calculate the Fresnel loss for if I know the refractive index of the fiber, if I know the refractive index of the epoxy which I am going to use for the fiber. So how it can be minimized? If your n is very near to n1. So it can be reduced to very low level using what we call index matching fluids or index matching gel between the gas. So use the epoxy whose refractive index is very near to the refractive index of fiber. So normally with the fiber we use the silica epoxy, silica resins, because it is a silicon. Fiber is silicon oxide, epoxies are also silica epoxies. So it reduces the Fresnel reflection. So index matching gel can minimize the Fresnel reflection, but it will not be zero. So Fresnel reflection is the one of the loss mechanism. Then another is the deviation in geometrical and optical parameters. All light from one fiber is not transmitted to another fiber because of the mismatch of mechanical dimensions. The mechanical dimensions of the fiber should match. When you are making a joint, the two fibers should be of similar specification. And what are the major parameters? One is the core size. Then we have the numerical aperture. So these are some parameters related to optical fibers. So this type of deviation may be because of the three reasons. One is the core mismatch. Then we have the numerical mismatch, numerical aperture mismatch. The core of the fiber may not be same. Similarly, if you are working with a gradient index fiber, the refractive index profile difference. I introduced one alpha parameter. Refractive index of gradient index fiber is your related to n1 into 1 minus r over a alpha. So alpha is the profile parameter. For parabolic fiber, alpha is 2. For triangular fiber, alpha is 1. For step index fiber, alpha is large. So there may be mismatch. Today, you laid your system today. Maybe after 10 years or after 15 years, there is a break in the system and you have to make a joint. And technically when you have to make a joint, your fiber will be damaged, maybe by the digging or maybe by some another means. So you have to prepare the fiber for the joint. You have to cut the fiber and make the fiber end very smooth, then you will make the joint. So in these process, generally we need around maybe 1 meter of fiber is required. This process. Or maybe you have to introduce some piece of the fiber. After 10 years or after 15 years, the specification of the fiber may not be same. I remember in the PC80 or PCXT. They came in the early 90s or late 80s, 87, 88 or 89. At that time they came with 30 MB hard disk. Today you go to the market and try to find the 30 MB hard disk. You will not find it anywhere except museum. And the cost may be very, very high. You may get gigabits capacity at lower cost. This is the scenario in the technology. Things are changing very, very fast. So same is the issue with the fibers. Earlier they were 62.5 micron multimode fiber. Now the standard is 50 micron. In single mode category, it may be 9 micron, it may be 8 micron, or it may be lower dimension. Dispersion shifted fiber, lower dimensions. So you need the same fiber. Numerical aperture. It depends upon the refractive index of core and cladding. It depends upon the purification of the material. The refractive index may be different. So numerical aperture may be different. So these are the some issues which need to be considered. So they lead to loss. A person who is assigned this job, he will make the joint. with the ingredient he has been provided. If fiber is not mismatching, is not of same dimension, it is not the problem of the skilled worker. So as a result, these are also the issues. So these type of losses, they are called the intrinsic losses. So losses due to Fresnel flexion, losses due to deviation in geometrical and optical parameters, they are intrinsic losses, and they are difficult to eradicate. So only way is that we should minimize those. So they can be used, they can be minimized, either minimized using fiber manufactured with lowest tolerance, or same fiber. I should get the same fiber after 15 years. How it is possible? So I have to keep the stock. If you look at the any OFC link, if you go around a OFC link, you will find they have put the marker OFC. Maybe concrete tower small, written OFC, or manhole. But is there in the manhole? It is a cable. They have left. So after maybe after 1 kilometer, they will leave 1 meter of the fiber, spare fiber. Out of 1000 meter, they are leaving 1 meter, say 10 meter, 5 to 10 meter of the fiber in a loop as a spare fiber. So maybe after whenever there is a need, they can pull that fiber and make the job. So this, because they know the problem and they have the solution for this. This is what first we should know the problem, then solutions are always there. So manholes, many companies, the technical designers, or they will take care that the same fiber should be available in future for joint. So intrinsic loss, then we have the extrinsic losses. So extrinsic losses are losses due to imperfection in supply chain. Here the skill of the person is required. Skill of the person is tested. The person should be very positive in making while making a joint. He has to be very, very careful. He should know all the safety measures. So this is due to misalignment. If your fiber axes are not aligned, you are making a joint. Mostly in the telecommunication system, you are making a joint of maybe 8 to 10 micron fiber core. The main joint is at the core to core. So you have to be very, very careful in making this joint. So this misalignment may be because of the different problem. One is a longitudinal misalignment. So this is a longitudinal misalignment. Your fibers are not coming near to each other. There is a gap, longitudinal gap. So longitudinal misalignment, there is a axis gap. Your central axes are not matching, they are offset. So we call it as a lateral misalignment or axial misalignment. Then there is a angular misalignment. Your fiber is at certain angle. So light will come and it will pass. So angular misalignment, that's why we need the fiber surface to be very, very smooth. Polishing of the fiber is the solution for the angular misalignment. We want cut to be a 90-degree cut and very, very smooth polished fiber. So these are three types of misalignment. So in that case, misalignment made in a single mode fiber, a misalignment of 1 micron offset, it may lead to maybe loss of around 40%. 1 micron is a very, very small measure. Simple calculation, it is the area of mismatch. You have a 10 micron fiber. If you calculate the area pi r square, so r square is 100. But if you are offset by 1 micron, so 10 micron will left with 8 micron. 8 square is 64. So 36% loss will be there. So it is a precision at micron level. So these are different type of loss. You see, this is the longitudinal loss. So longitudinal loss are least among these three type of losses. if your fibers are not touching each other, it's not going to make a major difference. Because you see, even up to 10 micron, the loss is around 1 dB. So very, very small loss. But lateral loss, it will be very, very large. So in this case, you see, the lateral loss is the axial loss. So axes should match with each other. So a small offset, maybe around 1 or 2 micron, that will lead to large loss for all these values. Then we have the angular misalignment loss. This is also very, very important. So here even a angle of say small, maybe 4 to 5 degree, that lead to a loss of maybe 1 or 1.5 dB. And again it depends upon the numerical aperture. If the numerical aperture is less, loss will be more. This is for 0.3 micron. This is a numerical aperture of 0.3. Then for numerical aperture of 0.22. You see, loss increases maybe by a factor of 2. So angle is very, very, I hope this 4 or 5 degree angle is very, very small angle. It is very difficult to make this angle using the compass and other parts. Normally in our middle classes we used to make, I think, 15 degree angle. इससे नीचे हम नहीं बना पाते. So this angle is very, very small, and we have to be very, very careful that it should not be there. So we need very, very say perpendicular cut and highly polished fiber, so that when you make the joint, they are completely sand based. So again, I mentioned about the Fresnel reflection. You can use the index matching gel, but when you use the index matching gel, you will see this is a loss 0.2. This is without air gap. This is with index matching gel. So index matching gels, they increases the angular misalignment, because when you put the index gel, you cannot polish it. So one have to see whether to use it or not to use it. So it depends how much loss you can compensate. So these are the different type of losses which are there at the joint, and one should be very, very careful while making the joint. There should not be any gap. There should not be any axial offset. There should not be any angle. It should be properly polished. So all these are the loss mechanisms at the joint. So once you understand the loss mechanism, then we will go for the different type of splices and connectors. I feel nobody talk about these connectors and terminators in your electrical system or electronic system, because their power is not a problem. But here it is very important. Splice and connector, they are very, very important, because we want very, very small loss. So it is important in the optical fiber, splice and connections. So it is a permanent joint formed between two fibers, just like a soldering. So two broad categories of joints. So one is fusion splicing or welding. So in welding, normally in the mechanical process, welding, we heat the two materials, raise the temperature to the fusion temperature or melting temperature, then we press them together. Same is the case in the fusion splicing. You have to heat the fiber to the fusion point, and you know, fiber, the fusion point or melting point is more above 1000 degrees centigrade. For pure silica, it is 1410 degrees centigrade. So you need very, very powerful heating source. So the heating sources are basically by applying localized heating, a flame or an electric arc. Some arcs are created where you can raise the temperature to very, very high degree. So at the interface between two buttered pre-aligned fiber end, causing them to soften and fuse. So you have to first prepare the fiber bring them together, align them together, and then you start the heating source. So you raise the temperature, the fibers they will start fusing, then you press them together. Then switch off your arc, then at the cooling the joint will be made. So this is how the fusion, this is the splicing and fusion splicing. So we use, these are different, you see in that figure you can see these two arcs which produce the high temperature, and these are the fibers put over the alignment platforms. These platforms they are on the micro positioner. So I can align within a range of micrometer, less than 1 micron. Mostly usually one is fixed, other is movable. So that when you heat, you have to press the two materials. Then only the joint will be made. So this is the fusion splicing. Then there is a mechanical splicing. So in the fusion splicing, you need a highly sophisticated fusion splicing machine, which has all these ingredients of high temperature, micro positioning, and pressing, and even all optical zooming and optical beaming, so that you can check whether fibers are aligned or not, whether fiber is properly polished or not. So these machines, they are the high cost instruments. Splicing machine may cost 4, 5 or even 10 lakh depending upon the features. In general, they cost maybe around 4 to 5 lakhs. So may not be available all the time, because the telecommunication, if you go for the Punjab circle, they start from Ambala and they go up to even away from the Pathankot, Gurdaspur, all these regions, they come under the Punjab circle. They may have 10, 15 or 20 machines, but it will not be sufficient to cover all. Any question? Okay. So all the time these machines may not be available for the splicing. So what is the solution? Nowadays, we want all our communication network to be always working. So as a result, we have to temporarily make the joint. My system should be in the running position. It may not be at high performance, but it should be running at least. I will be satisfied if it is running. It should not be at break. So the provider, we have the mechanical supplies. So one can go at the particular site, take out the fiber and use some mechanical splicing. So mechanical splices are basically fibers are held in alignment by some mechanical means. I can use a very fine narrow tube, what you call tube splice. I can put the two fiber in a very fine capillary, maybe of the diameter around 130 micron. My core cladding is 125 micron. I can use a fine capillary so that I can put the two fiber there. So it can be a tube splice or it can be a groove splice. So in a tube splice you have to put the fiber, whereas in a groove they are mostly B groove. So my fiber can align here. The area of contact in this case will be very less as compared to tube part. So damage or pressure on the fiber in the groove is always less than the tube. So same we have in the cables. It can be a tight buffer, it can be a loose buffer. Loose buffers has advantages than the tight buffer. So we can check it, you can see. But the fiber must have smooth and square end faces. So while making whether it is a mechanical splice or it is a fusion splice, you need the end faces to be very smooth and square or 90-degree angle. So what is called the end preparation. So end preparation is very important in the fiber. You have to cut the fiber, and you know the fiber is made from glass. I hope everybody has seen the glass cutter. They use the diamond cutter just to make a line over the glass, and then they apply the pressure. You cannot cut the glass by rubbing again and again. Only line is sufficient. That will give you a best cut. So this is what is, so for this purpose we can have either what you call as the cleavers. Cleavers are for 90-degree cut. They are the normal devices where you can use the cleaver, or manually you have to scribe and break. Just make a line and then break it, or what you call score and break. So for this purpose, scoring of fiber surface under tension. So we put some tension over the fiber, then score. This tension will automatically lead the crack. So for this purpose, I need the tool, cutting tool. Normally, in any machining tool, the cutting tool should be harder than the material to be cut. So we use sapphire or diamond or tungsten carbide blades. These are the materials harder than the glass. So we can have this cutter. This is how you can put the fiber under certain tension, then apply the cutter and then apply the force at the two edges. So crack will be, now cut will be very fine. It needs practice. The skill will be tested on this part. So after practice, one can cut it very easily. Because all the time cleaver may not be available. A cleaver may cost maybe from 25,000 to 30,000. It has all those fine features. But a normal diamond cutter, it may cost maybe few hundred rupees. So mechanically, sometimes one have to find out the solution. So these are the type of cleavers. You can see this is a one cleaver where you have to just remove the fiber. From the fiber, you have to remove the outer tubing. You have to cut the Kevlar. You have to remove the buffer, and then you have to cut the fiber. If the fiber is with the coating, you have to remove the coating also, because coating will come to the surface then at the interface. So we have to remove the coating. If it is a bare fiber, we have to remove the coating also. So joint is always between core and cladding, because cladding you cannot separate. Core and cladding are required. So this is a cleaver. This is another number of type of cleavers are available in the market. So depending upon the requirement, depending upon the features, one can have these cleavers. So just you can see you need different type of tools. For example, if you have this fiber, you need the tool to cut it. You see, this is a bun. We call it as a stripper. So you have to remove the outer part of this tube using a stripper. Okay. Now you have only buffer. So buffer can be cut with fine narrow. So sometimes it is available in cleaver also, but you can use, depending upon the requirement, you can use another cut which will remove the buffer. So with this part, I can take out the fiber. So now you can see the fiber at the outer part. So if this fiber is coated, then I have to again use the cutter to remove that coating, and ultimately we have to reach at the fiber. So this is required whether it is a fusion splicing or it is a mechanical splicing. You have to reach at the core and the cladding. So for this purpose, one needs some type of skill or some training is required for this purpose. So then once you are ready with the fiber, then you have the cut is there, then you need the polishing, so that there should not be any angular misalignment. The polishers, this is some type of abrasive. So you can polish the fiber over the abrasive, and then the surface will become smooth surface. In mechanical this is called buffing. So buffing is just the rubbing. In the market you will see these automobiles, कार को पॉलिशिंग करने के लिए they do some buffing और आपकी गाड़ी लिस्क जाती है उससे. So this is same process is required. So we need this can be also manual or some equipment is also available. We call it, these are the polishers. So mostly they are the multi-pack polishers. For single fiber, you can go for this process, but when you have multi-fiber cable, 24, 48, 96, it will take long time. So in that case, these polishers are very helpful. All the fiber bundles you can put there, and it will polish all the fiber in a single instant. So polishers can also be used for these applications. So cable preparation. So then we have the fusion splicing. So after your fiber is prepared, you have cut the fiber using the cleaver, you have polished the fiber, then you will come for the splicing. So the splicing here you will see in this diagram, your fiber is prepared, and you can put the fiber over this. This is one block, this is another block, these are two electrodes, and they are over the micro positioners. So once you are ready with the fiber, the fiber and surface, they are prepared for the joint, then the heating of prepared fiber is required up to fusion point, and then you have to apply the axial pressure. So when the fiber they come very near to each other, then you have to stop the heating, and then within small time, maybe after 1 or 2 minutes, or maybe depending upon the time, the joint will be ready. The fiber will get hardened. So it requires positioning and alignment using microscope. So you can check under the microscopes also, under the magnifying. So earlier there used to be what you call the mechanical splicer. You have to check all these parts. You have to prepare the fiber, you have to check the alignment, all parts need to be checked by the manual. So it takes long time, and also high training is required. Highly skilled person is required for this supplies. But then now we have the computerized machines, automation. So in that case, fiber end preparation is not very important, but cutting of course is important. So this is a 4-stage process. No need for end preparation. So in that category, you will see you cut the fiber. It may not be 90-degree cut, but at least better the cut, better will be the supplies. So in the first process, you cut the fiber and put the fiber at the positioning platform. Then one start the electrodes, not at very high temperature, maybe to the temperature when fiber get softened. So we know the fiber end, they will take the circular shape. We know the phenomenal surface tension, minimum surface area. When you heat the material, when they melt in the liquid, go to liquid form, they take the minimum surface area. So in that case, you will see they get fused and they will take the minimum surface area. So now it is easier to match the axis. So they get smoothened, and at the next stage, the temperature is further raised. So now in that case, they get fused, they get very softened. Then automatically the machine, it will press the two fibers, and then once this is what you call the electric arc, applying the arc. So arc will be applied, then it will be stopped, and within a small time you will see the fiber will again get hardened after removal of the arc, and the joint will be. So in this case, it will be an automatic operation. Automatically it is a computerized, it is a software which will perform all these calculations. So these machines, they will check for all this. It is a 4-stage process. Polishing or end preparation is not required or not very important in this case. So we have different type of machines. They have the splicing. It has a small Fresnel reflection because interface is with the fiber material. Although it is fused, but refractive index is more than the air. So N1 minus N will be smaller in this case. So less smaller Fresnel reflection, and typical loss may be less than 0.1 dB in this category only. So you see, these are the different type of fusion machines. This is a closed area, so you can have an open view. So you have to cut the fiber with a cleaver and put the one end of the fiber in this area, another end of the fiber in this area, and you will see these are the two electrodes. And when the fibers are placed here, you have to cover it with a cap. In between these, there are the CCD cameras. All viewing is there. So when you close the cover, you will see everything will come on the monitor. The monitor, it will check the cut in the fiber, it will check the alignment, both X and Y alignment. Then the joint will be, once the fiber ends are fine, then the arc will stop. So you have to, initially you will find different switches on this. Once you position the fiber, you have to press the set button. So it will check for the alignment and cuts. After set is passed, you have to press the arc. So it is a two-stage process. Once arc is there, so it will take some time. So all these processing is required. And at the end, it will give how much is the loss at the joint. There is a sensor which will measure how much is the loss in the joint. Maybe 0.05 dB or 0.08 dB or 0.02 dB. It all depends how you process the joint. So splicing machines are there. So then after the fusion splice, now you see, when you have one fiber, you have another fiber. You have fused the material, and we know all these materials, they have some expansion coefficient. When you heat, they expand. Now their area will be moved. So you will get these type of bulging, the extra material that will take this type of shape. And now this is a fused material. When you heat any material and when it again comes to its normal position, it loses its strength. So the drawback, the fiber get weakened near the splice, maybe by 30% or more. So as a result, the fiber may fracture near the splice. It may fracture because it is not now fully, it loses its strength. It is not very strong at the joint. Normal fiber is very strong, but at the joint you have heated the material. So as a result, you have to splice you have to provide the protection to this joint, what is called splice packaging. So splice packaging is to reduce the tensile loading over the fiber. If afterwards there is some pressure on the fiber, the joint may break. But if it is packaged, we will use some different type of sleeves, protection sleeves, that will protect the joint. So depending upon if they are the same fiber, you will get the bulging. If they are of different fiber, sometimes you have to join the different fiber. For example, in the case of regular fiber and amplifier, erbium doped fiber amplifier, in order to get the optical amplification in EDFA, the dimensions are not 8 micron, because you need high interactions. The dimensions may be 4 to 5 micron. So when you are making these type of joint, you will get this type of tapering also. Material get dispersed. So we need these are the protection sleeves. So before making the joint, you can put this sleeve over the fiber, and when the joint is ready, you drag the sleeve to the joint. And now these sleeves, they are very specific material. When you heat these material at a temperature maybe more than 250 degrees centigrade, they will lock up there. So you bring the fiber to the joint and put it under the heating place, and they will get locked up. So after you remove the heating, they will lock up there, they get hardened, and now your joint is fully protected. So we have this type of sleeve, you can see here. So we have this cable. So we have taken out it here, brag, and in between there is a splice. So this is a fiber. So this is a protection sleeve. So after making the joint, we first put it over this cable. After making the joint, we brought it here and then we put it under the heater, and now it is locked here. So now fiber will not break. It is very, very hard. It will not break now. If you will not use the sleeve, there are the very high chances of breakage. So protection sleeves are very, very important after the supply. So these are the different protections. Now it depends. You see, if it is a single fiber, I can use a single protection sleeve. If it is a multi fiber, we need number of splicing. So sometimes we have, these are the protection sleeves. These are the fiber trays. If you have a multiple fiber, after the splice, you have to arrange them. You cannot leave them as such. So they are put on particular type of housing. You see, this is a maybe some 6 slots tray. It may be 6 slots. There may be 12, 32, 64, depending upon how many fibers are there. These are called splice trays. So you can make a joint, put the splicing tube, and then it can be put like this. You can give a roll, and you can see 1, 2, 3, 4, 5, 6. 6 fiber can be arranged like this. This is normally for the underground. When you have an underground some splice enclosure, one can put these trays there. But sometimes you see fibers are aerial fibers. So in those cases, the joint will be outside. It will be exposed to all type of environmental variables. So then we use these type of enclosure. This is a fiber joint enclosure in the outer space. So now you will see, whenever you go along these fiber, which are the aerial fibers, you will find these type of black color cylinders. Some cylinder hanging there. It means there the joint has been made. These cylinder, they have similar type of, this is the inner view. These are different trays. You can align the fiber along this, and you can put this over the cylinder, and this is a very, very hard material. All hard plastic material, and it will not be affected by environmental parameters. So your joint is safe now. So it is not only the joint splicing. You have to see that your splicing should be safe. So these are the different type of the splicer. Fusion splicer. So whenever fusion splicer is not available, then in those cases we go for the mechanical splicing, which uses accurately produced rigid alignment tubes or sleeves or grooves into which the prepared fiber end are permanently bonded. It may be permanently bonded or temporarily bonded. It depends your approach. So mechanical splicing, I mentioned, it is either a tube splicing or it is a groove splicing or loose tube, like tight buffer and loose buffer. So it is called snug tube splice, it is called loose tube splice. Your tube may be circular or it may be rectangular or it may be B groove. There are the benefit of one over the other. Because when you are putting your fiber in a very, very fine capillary, there are the tolerance problems. When you are inserting your fiber, it may rub with the surface. The rubbing may lead to some sort of the maybe micro bending or other pressure on the fiber. It may damage the prepared surface also. So in that category, loose tubes are better or B grooves are better. So you can see just the comparison. Snug tube supplies exhibit problems with capillary tolerance. The losses may be up to 0.5 dB with the tube supplies. Whereas in the loose tube, there is no tolerance problem. And losses may be less than maybe 0.1 dB with loose tube. Because the axial pressure on the fiber is not there in the loose tube. It is free to move. So pressure will be borne by this movement. So this is one sort of the ultra supplies. You can see here. This is you can insert your fiber from this side, You can insert your fiber from other prepared fiber from this side, and in between there is a glass window. So through this glass window you can see whether the fiber has come near to each other or not. The diameter of this tube, you see, the diameter of this tube is very near to diameter of the fiber. If it is a 125 micron cladding, the diameter may be 130 micron, so that there is no axial offset. There may be gap because longitudinal loss is not very crucial, but axial is very crucial. So we have these type of supplies. We call these as ultra supplies. It can be a reusable supplies, or it can be a single usable use supplies, depending upon the approach. So we have one supply here. You can have a look to see. This is a ultra supplies. So you can see it. Just it has two sides, and this is screwable. I can loosen it and I can insert the fiber. I can loosen the another side. I can insert the fiber from this side, and in between there is a window. So I can see when the two fiber come near to each other, then I will tighten it. So fiber will be locked at this place. So I can leave it there. So whenever my splicing unit is available, I will file a complaint with the splicing unit. They will come to that site and they will replace it with the permanent splice. So it can be reused because we have used only the screw. So sometimes we have the another splice which is not reusable. Now here it is the same another type of splice. It is a very fine capillary. So I can insert the fiber from here. It has a place for epoxy. I can put a drop of epoxy before inserting the fiber. So one fiber inserted from this side, other fiber inserted from this side, and they will be fused, they will be joined by the epoxy. But in this case, once you use the epoxy, you have to break it if you are going to replace it with the permanent supplies. So it is a single use supplies. So these type of mechanical supplies are also used. They can be. There is an option because mechanical is a temporary. Temporary can be made anytime made permanent. That's not a. That is your how you follow. So here the losses are also maybe around 0.2 dB. So very near to the permanent splicing. So if it is more than one, there is a need for permanent splicing. So then we have the groove splicing. So in the earlier part, the capillary is circular. So there are certain tolerance problem. So in this case, we can have a B groove. The fiber will come at this point. So now it will touch the groove only at the two places. So the axial area will be reduced to one half. So in that case, we can use the groove for better alignment and lesser axial pressure on the fiber. So this is a B groove. You see here B groove is formed. I can put the fiber. I can put the cover here. So B grooves minimum contact with the substrate. Then I can have what is the elastic tube. They are elastomeric supplies. In the B groove, the fiber is loose, so we can use some elastic material. So in the elastic material, it will automatically adjust the pressure on the fiber. The another benefit of these type of elastomeric part is that they can be fiber of different diameter can be centered and hence successfully supplied. If the fiber is of larger diameter, the elastomeric material it will adjust. The pressure may be somewhat more, but it can be used. So here also the loss is also of the order of 0.2 to maybe 0.1 to 0.2 dB. So elastomeric is another solution. And normally you see elastic materials, they are more expensive. So they add to the cost. So we can use what we call as the springs, spring groove. So this is a spring action. So spring will automatically adjust with the dimensions of the fiber. So we use the springs here. This is a spring. So we have the fiber, the spring will adjust the pressure on the fiber. So here also that is another option. So in all these cases, so in the mechanical splicer, you have to take out the fiber, you have to cut the fiber, you have to prepare the fiber. And it required lot of skills, lot of time consuming also. And when you have cut the fiber, you have to polish the fiber. And you know fiber is 125 micron. So during polishing, there are chances of breakage. So to avoid that part, we go for what is called the secondary alignment technique. So in this technique, we will first the alignment of secondary element around the bare fiber. So we have the fiber. Over the fiber, we will put some ferrule. So like this, in this case, if you see the fiber, some ferrule is there. So we will put some ferrule over the one fiber. One will put ferrule over the another fiber. So now these ferrule can be very easily polished. These ferrules are made from any hard material. It may be a ceramic ferrule, it may be an aluminium ferrule, it may be a stainless steel ferrule, it may be a brass ferrule. The cost will vary, but it increases the ruggedness. Now ferrule will not break, and easy to ground and polish the fiber end, and better termination. Only drawback is it is more time consuming, because to put the ferrule you need some time, and when you put the ferrule you have to use some epoxy also. It will also take some time to dry up. So in that case it is time consuming. It increase losses due to tolerance on the secondary element. If your alignment is not very fine, it may lead to losses, because you are putting the ferrule and central alignment element. So but it helps to increase the ruggedness. So here you see, here in this case you have a fiber, we put ferrule over one fiber, there is a ferrule over the other fiber, then these two ferrules, they will be aligned in the misalignment. This is just like a linear connector. So I can put the two connector in a linear sleeve. So these two ends, they will come inside and they will be aligned here. So fixing of alignment sleeve or of metal or plastic, it depends. So here this is another option. The losses are also taken care that they should be as small as possible. So these ferrule and alignment sleeve, they have to be very precise. High order of accuracy for the alignment. If there is no alignment, that will lead to more loss. So we have the secondary elements alignment. Similarly, I discussed earlier, we can have a rotary splice. There I can rotary splice, basically you will see they are the glass ferrules, but alignment sleeve within the sleeve which can be rotatable. So you put the ferrule and bring them to in a rotatable position. Where there is a maximum power, you can lock it there. So it is done alignment. Here it has a built-in offset and rotation for excellent alignment. Alignment accuracy of 0.05 micron using 3 glass rods, and loss may be very small, maybe 0.03 dB using the index matching gel. Here you can also use the index matching gel, because rotation is there. So rotary splice. So then we have the multiple splice styles. If you have a multi-core fiber, either you align, you make a splice of 1 by 1, or you should have a technique of making the joint for all the fiber simultaneously. So multiple splice, they are commercially available for number of fibers, Simultaneous splicing of 5 fibers may be in the 5 minutes. Okay, and 15 minutes for 5 single fusion splicing. So individually, so for single, if you have a 5 fiber, it may take 1, so 5 into 5, it may take 25 minutes. But for multiple splicer, it takes very small time. Loss may be somewhat more, but it takes if you have a 96 fibers, if 5 minutes are required for each splice, how long it will take? Now you have a splice with a groove of maybe more than maybe 12 or 24 or 32. So you can make a 96 fiber splice maybe in a three steps. So this they have the benefit. Loss is somewhat more, but not the alignment can be, because when you are aligning a single fiber, the alignment will be very you are focusing on one alignment. When you are aligning the 4 fibers simultaneously, so all the fiber cannot be aligned to all great accuracy. So somewhat misalignment, but it gives the reasonable good, reasonable small loss. So multiple splices are also there. So this is how we put. Mostly they are used with the ribbon fiber. So we have to put ferrule over the fiber. We need a substrate where fiber can be put. So all the fiber in the ferrule, it has a substrate, so they can be aligned like this. You can see here, you have put the ferrule over the fiber. All these fiber are the ribbon. Number of fibers, ferrule on the another multiple manner, then they can be put over the sleeve. The sleeve or substrate should have also the number of channels equal to the number of fibers, and ultimately they can be locked together. So multiple splices are also available for all these applications. So similarly, we have the connectors. Splicing is there because at all the time splicing will not serve the purpose. At some places we need the connectors. So connectors are also of mostly demountable fiber connectors. The requirements are same. Minimum loss at the connector with all these tolerances. So more difficult to achieve than fiber splice, because splice is once. Connector many times. You want the reproducibility. The connector can be mounted maybe 500 times or 1000 times. So all these are the factors. Must maintain similar tolerance requirement, but in removable fashion. Must allow for repeated connection and disconnection without problems of fiber alignment, without degradation of performance. Must protect the fiber end from damage due to hand, because in that case you are when you are taking out the connector, the fiber will be in the outer part, will be exposed to external environment. So during that part, the fiber should not damage in the field application. So something should be there at the connector so that fiber should not be exposed. Must be sensitive to environment factors. Moisture, dust, they should not deposit at the fiber. Must cope with tensile load on the cable and can be fitted with relative ease. If there is a pressure on the connector should have strength to bear that pressure. Even sometimes in the exercises, especially in the military application, while they are practicing, they laid their link. Even their military vehicles or tanks, they pass over these fibers. They should not break. The connector should have that much strength. I know one case, there is a unit ordnance cable factory in Chandigarh industry area 1. One fellow, Mr. Kulwant Singh, he made a connector for military application with the optical fibers, and he was awarded with the President Medal. That was the importance of that connector. So they are very important, and ultimately should have ideally low cost component, because number of connectors are required. They should not add heavily to the cost. So all these are the different connector part. So these are the additional requirement of the connector as compared to supplies. So as a result, we have three major parts in the connector. One is the fiber termination. It protect and locate the fiber end. I should be able to see where is the fiber. When you are going for the alignment, I should be able to see where the fiber is. So for example, in this category, so I know the fiber is at the center of this ferrule. Then fiber end alignment. I have to align the fiber. So there are different places on this connector. This is the end alignment, some line is there. So only it will follow the alignment. So there are the receptacles. So when you are making the connection, it will follow that particular alignment. So some mechanism should be there for the alignment. Then outer shell. So it maintains the connection and fiber alignment, protect the fiber end from environment, and provide adequate strength at the joint. So all you see, there is the outer shell also. Sometimes it is a BNC type, sometimes it is a screwable, sometimes it is a push-pull type of connector. So all the connectors, they have these three terminations, three components you will find. So we have different type of connector. You see, number of connectors are there. You see, this is a SC type of connector, this is a SC type of connector, you see another LC type of connector. All these connectors, you see the tip, all the tips, you see the inner alignment sleeve, and you see the outer shell. Outer shell is free, I can screw it, because ultimately it has to be packed. It is not a loose connector. ये नहीं है कि आपने कनेक्टर लगाया 5 मिनट के बाद बाहर है. How do you connect your fiber to the repeater? You cannot fuse your laser. How do you connect your fiber to the optical source? Not in between. Your fiber has to be terminated at some point. For example, I have a direct interface on the computer which attached the optical signal. I have to connect fiber to my computer. I cannot fuse there. So connectors are at the termination end. You have a patch panel. Number of connectors are put there. There it cannot be spliced. Splicing is only fiber to fiber. Connector is with fiber to the device. Okay. So we have number of connectors. Mostly we call these are the butt jointed connector. So you see, this is the SMA. Here you see the fiber at the center, alignment, then nut type arrangement. This is your ST connector. This is a BNC type locking. This is your biconic. It is a spring, push pull. Similarly, this is a FC type. This is the inner part, inner shell, then outer it is a screwable. So all are the different type of connector. I have brought some of these connectors. You can see some type of cables, or you see this is one, the ST connector. It is a ceramic and then BNC type locking. Similarly, we have another type of cable. Like you have this is your FC type. So you have this ceramic ferrule, another layer, and this is loose. This can be screwed on the receptacle. So similarly, we have the SC type of connector. So it have another arrangement. This portion is loose, so I can push this connector. Okay. So number of type of connectors are there depending upon the designer, depending upon the company also. So this is also this is the LC type of connector. It's very fine alignment. This is a cable with LC type of connector and with FC type of connector. Sometimes you need the interfacing. The companies who are providing the equipment, it depends what type of connector they are using. They may not be using the same type of connector which is available with your cable. So in that cases we need some sort of interchangeability or adapter compatibility. So I can use a patch cord with different type of connector. So all different type of connectors are there in this category. You see, one approach is butt joint, to bring the two connectors near to each other. Another is the expanded beam connector. Why we need very fine alignment? Because fiber is very narrow. Now if I expand the beam, now it is quite larger in size, there is no problem of misalignment there. So in this approach, one use the fiber, one use some optical element or lens. It will expand the beam, then it will become a parallel beam. On the another rule, there is another lens which will focus it on the fiber. This type of technique is used. Mr. Bhatnagar, he was also discussing how to align, how to make the beam narrow. So same type you can use this. So here now the beam is very large in size, maybe 1 millimeter or 2 millimeter. Here 1 micron is not significant. So it is another approach. So number of type of connectors are there. I will show you. You will see this is a glass ferrule connector. You see this is a fiber and this is a ferrule. So this ferrule is another ferrule. They are put in the alignment. So ferrule they will touch each other at this point. So this is the one end. You see fiber and then ferrule. So we put one here, but is called here. You see the adhesive and you see body. This is a written here is bath joule. What is the bath joule? Bath, you have the baths. What is the joule? You will find on your baths is written 7 joules, 12 joules, 17 joules. Earlier baths used to be the mechanical baths. Then joules were very important. But now they are from quartz. But still you will find some components there. Bath joules are basically very fine screws. These screws they are made from very hard material, sometimes from diamond, because there should not be any wear and tear in these screws. Otherwise, time will vary. So and bath joule. So I mentioned when you put the ferrule over the fiber, you have to polish it. So during the polishing, your fiber is made from the glass. If your material is softer than the glass, it will also get rubbed. So one put the diamond joule here, bath joule. So diamond will not rub, only fiber will get rubbed. It's very useful in polishing process. So this is the bath joule for close and approach and tolerance requirement. Even if you ferrules they come near to each other, the fiber will not be damaged because there is a bath joule. So cylindrical ferrule, then this is a ceramic capillary. Your ferrule may be of glass, it may be of aluminium, it may be of any metal, or it may be of the ceramic material. Ceramics are the best material. They have the best outstanding performance. Ferrules from ceramic, they have highly very good thermal properties. They have very good mechanical properties. They are highly chemical resistant. So mostly ceramic ferrules are, but on the other hand, they are expensive also. A ceramic connector will cost the most. So one have to see all these factors. So ceramic capillaries, so you will see different type of connector. You see all these are in different categories. I have shown you different. This is the SC connector, this is the FC connector, this is the SP connector, this is the SMA connector. So many type of categories are there. But all you see, they will be of different component. It looks a single part, but basically each connector you will see the 3 parts. So I will, although they have been shown in the expanded form, I will show you maybe one of these connector. You will see it has 3 components. This is the one part. You have to put this over the fiber. Then you have to take out the fiber from the cable, and then we have to put the fiber through this ferrule. The fiber will come at the end, at the tip. The fiber will come. So when fiber will come out, you have to put the epoxy so that it get locked there, it get joined there. So once fiber is put, so I will bring it here and it will be locked. I can use some clamp tool to press it, so it will be locked. So ultimately your connector will look like this form, this type of connector. So it is a process. One have to learn it. One have to practice it. So it is not a simple just putting a 2-pin connector over the electrical wire or 3-pin connector over the electrical wire. It needs lot of practice. It needs time also. It needs lot of skill. So also there is now we also provide this training at our last month we conducted this program for skilled worker. There is there is a NSDC, National Skill Development Corporation. The part of this is a TSSC, Telecom Sector Skill Council. They identified under this area there is a skill optical fiber supplier or optical fiber technician. They should know how to splice the fiber and how to test the fiber. So we conducted this 1-week program for the trainers from TSSC on fiber optic splicing and testing. So they learned how to make a splice, how to put a connector, and how to test the fiber using OTDR. OTDR we will discuss on Friday. So they have their importance because they need the skill, and all these fiber optic company they need expert for these supply chain. There is a lot of requirement. They have identified there is a lot of requirement of skilled worker in this area. So it is not simple, it needs practice. So different type of connectors are there. I shown here. So another type of connector. Then similarly, I can like our rotary supplies. We can have double eccentric connector where it comprises of 2 cylinders which are rotatable. So we can align because connector mostly we perform under some alignment. We send the power and we see when maximum power is delivered. So it consists of 2 eccentric cylinder with outer ring and so on one you have one fiber, you have the another fiber. Just you align it like this. How much distribution is required? It can be 50-50, it can be 60-40, it can be 80-20. So same it is possible because fibers are very thin. Then similarly like splicer we have a multiple fiber connector. If you have a multi-fiber, you need the connector. It is the same type of arrangement. You need the ferrules with multiple slots, then alignment sleeve with multiple grooves, and then they can be put over the fiber, one fiber, another fiber, and then they can be locked together. They have the metal guiding rods and coil spring for alignment. So multi-splicing is also there. Average loss is again maybe around 0.8 dB or 0.4 dB if you use the index matching fluid. Fresnel reflection can be reduced because inherent losses will there be in the connector also. So these are the different type of butt joint connectors. Then we have the expanded beam connectors I already mentioned. So they utilize expansion of the beam. So now you have a large beam, small micron offset, it will be insignificant. Out of 1 millimeter, if there is an offset of 1 micron, it is insignificant. But out of 10 micron, if it is offset of 1 micron, it is very, very significant. So that is the approach here. So one can use here what we call as you have a fiber, you use the micro lens. These are very, very fine lens. maybe diameter of 50 micron. So you can put one lens over the fiber, one ferrule, another on the fiber, and then bring them together. In that case, alignment sleeve is not required because beam is larger in size. You can see the beam very easily. So you can use the two lens, or you can use a lens in the alignment sleeve. Here lens is, you bring the fiber end should be at the focus of this lens. Similarly, another fiber. What is the benefit of using single sleeve here? Any guess? Here I am not using the sleeve. Here I am using the sleeve. So in this case, the losses will be less, because when the light pass through any material, there will be loss. Now here it is passing through two lenses, so loss will be more, 2 times. Here it is passing through one lens only, loss will be half. There may be offset for alignment, but power absorption will be less. You can improve that. Alignment can be improved, but this loss cannot be improved. So we have these type of lenses. Here the average loss may be around 1 dB. It can be reduced to 0.7 dB using anti-reflection coating. The loss is because of the coating. The fiber light is coming, it interacts with the lens, some portion will be reflected. If you use the anti-reflection coating, the reflection will be less. I can improve the loss. I can use what you call as the green rod lens. These are gradient index fiber. So they will get the autofocusing. So here you see this is an alternate lens geometry. They are very efficient. They will give the focusing action to the fiber. So roll from the gradient index waveguide. They are very fine, 0.5 to 0.2 millimeter diameter, and the light propagation is determined by the dimensions of the lens. How the lens is cut, how the lens is made. It can be a focusing lens, it can be a defocusing lens. It depends upon the dimension of the lens. So they used to produce highly collimated beam and in sinusoidal path. When it is straight path, it will not, either it will be diffracted or it will be converged. But when it is different path, you can, from the same lens, you can get the focusing or you will get the defocus, depending upon dimensions. So you see these are the rods, they follow, this is what is the path. I will not go into that part. This is the equation for this lens. So this is the solution. You see, this is a cos and sine. So this is a sinusoidal path. So one sine cycle we call it as a pitch. Normally wavelength, one cycle. Here it is, we call it as a full pitch, one cycle. So there can be different pitch. I can control the pitch of the lens. So various fractional pitches are possible. This is a 0.25. From same lens, in this direction it will give the focusing, in opposite direction it will give the parallel beam. But here it is focused at this. This is a 0.25 lens. Similarly, this is the 0.23 lens. What is the difference in two? Your fiber is at certain distance. There is no need to sandwich the lens over the fiber surface, because during this process your surface may get rough. But in that case, the lens will not touch the fiber surface. Then now in this case you need the two lens, one lens over the fiber, one fiber, other lens over the another side. So I can add another which is 0.29 pitch lens. This lens, it will give both the actions. Now these type of lens, they are used between the alignment sleeves. Now only one lens is required. So you can bring the fiber here, it will follow this path and it will be focused on the another fiber. So different pitch lenses are available, 0.25, 0.23, 0.29. They give the focusing actions. Then now they are available from company Cellfox. These are Nippon company. They are the same material which are we use normally the contact lenses. It's the same Nippon company, and the losses are around 0.1 dB, around 1 dB. These type of lenses, mostly expanded beam connector, they are used when fibers are coupled to PCBs because they are larger devices. So in that case, you can expand the beam and you can connect it. So graded next lenses, they are also important for connectivity applications. So losses can be further reduced to different values. So for all these applications, we need different type of connectors, different type of adapters. Sometimes you have a SC type connector, you have a SC type connector. So in between, you can use an adapter, which is here it is the SC type, here it is the another type. So that solves your problems. We need number of reels and number of patch cords to connect one instrument to the another instrument where the connectors are not compatible. So patch cords are required. All patch cords are available. I showed you this patch cord. You see it has SC type connector, it has FC type connector. So I can connect it to a device which has FC type connector, it can be connected to a device which has the SC type connector. Otherwise, you cannot connect SC and FC. So all these type of patch cord cables are required and they have to be made. They are nothing but they are the connector. So all this one have to learn. And for making all these, we need what we call as the fiber splicing and connectorization kits. To start any work, you need the tools. So these are the tools for all those applications. One should understand these tools. You need the cutting tools. You need the microscopes. You need the epoxies. You need the cramping tools. You need the optical power, optical source or optical detector. You have to check the patch cord. You have put the connector, you have to check its performance. You have to mention what are the losses in this patch cord. So all these checkings are required for different applications. So splicing and connectorization kits are also available, commercially available. So one should be familiar with these components. So I will stop here. So I have given information regarding the joints. Joint category, we discussed what are the different loss mechanisms. There are the intrinsic losses, there are the extrinsic losses, and one have to take care of those. Our requirement is that the loss should be minimum at the joint. We discussed the different type of splicers, then of course different type of connectors. They are available in different varieties, in different cost. So one have to see, because I mentioned our communication system is one requirement is the economy. It cannot be very, very expensive. So one have to look for all those solutions. So I stop here in case you have any query or any doubt.